Hello everyone, my name is Laurent Georget and I'm presenting you today the Kayrebt toolset, and more specifically one tool from the Kayrebt toolset, Kayrebt Viewer. So here I'm in my projects directory where I can see all my Kayrebt projects. Kayrebt Viewer is a visualizer for activity diagrams. What I call activity diagrams are a subset of UML2 activity diagrams. They are a representation for C source code. So let's get on it and launch the application. The first window we are presented with is a preferences dialog to configure the application. As we can see, we have three settings. The first one is the location of the codebase we want to analyze. The second setting is the location of a symbol database, which is a simple table of global functions in the codebase. Finally, the diagrams directory where the activity diagrams have been generated for the current project. In our case, we want to explore the Linux kernel version 4.1, so we are going to select it. Here, and here we see all the directories from the Linux codebase. The symbol database was previously generated, so we are going to select it. Finally, we are going to select the diagrams directory where the activity diagrams have been previously generated for this version of the kernel. Here we see that the directory mimics the layout of the codebase directory itself. We have a directory for each directory in the codebase, and for each compilation unit we have a directory which goes by the same name. Each of these directory contains the diagrams files for this compilation unit. We can see them because of the filter. So we are going to select the entire diagrams directory, and here we go. So let's open the application. Okay, we see here the main window with three panels. The left panel, the central panel where the diagrams will be displayed, and the right panel. It's possible to open a diagram from the menu. We are presented with the diagram directory we selected earlier. So let's say that we want to open a function in the fs submodule. Here we go. For example, one of the functions involved in opening a file. So we go in readwrite.c, and that's vfs read dot. Okay. Here we see an example of a function. By convention, each activity diagram represents one and only one function. So we can zoom in and out, we can drag the diagram. So, by convention, there is one init node and one return node. We have three types of nodes. The diamond ones are decision node, so binary conditions. The square nodes are affectations to known variables, so for example local parameters or local variables. And the ellipses are everything else, so function calls or as we can see here at the bottom, affectations to temporary or anonymous variable. The representation we see here is quite low level because actually we plugged us in the JCC compilation process. So what we see is one of the representation JCC maintained to compile the code. So the code here is in 3 addresses mode. This low-level representation is useful for several reasons. First of all, it's a very simple representation. The code is in 3 addresses mode, all conditions are binary, so it's very easy to follow. And another useful feature is that you can see the entire control flow at a glance, even for most complex function. Here, for example, we see the condition, another condition, etc. The error handling code seems to be on the left branches, etc. We have several controls to interact with the diagram. For example, hovering a node highlights all nodes reachable from the hovering point. So it can become a bit messy with loops, but usually it's very useful to understand the error handling code. And another useful feature is the ability to get rid of uninteresting branches. When I double click on a node, I remove the branch altogether. That is, I don't remove the nodes which are reachable from another branch in the code. Of course, there is a way to reset the diagram using the contextual menu. Let's close this diagram. We are going to move on, but first I want to show you a bit more of the interface. Here we have a history tab which gives all the diagrams which have been explored so far. So here we have explored only one diagram, VFS read. We can click on those entries and it reopens the diagrams. Of course we can get rid of entries in the history with the contextual menu. The other tab is the symbol database, the very same symbol database we selected earlier. So in this table we have a function for every global function in the source base. This table can be sorted by column and filtered. So, for example, this supports multi-filtering, actually. So, for example, you can search for the read function in the fs directory in file starting with read, write, etc. The field supports regular expression filtering. On the right side of the window we have the source tree view, which is a simple view of the source directory. So here we can see all the source files and also objects file because I did not clean my source directory. The two panels are interconnected. So for example, if in the tree view I select a file, it updates the two filters on the left. It's more obvious if I clear the first one. So for example, if I select a file, I see all functions exposed by this file. This works the other way around too. If I select a file here, for example this one, there are two effects. It selects the file in the right panel. It's more obvious if I choose another file. For example this one. And it opens the diagram of the function in the central panel. Now I'm going to make a complete example. First let's get rid of the history and the open diagrams. Here. Okay. So let's say I want to check on a particular system call, kill for example. Kill is used to send a signal from one process to another. I look it up in the database. Here it is. And let's say that our objective is to get more insight on its internal functioning, where the security checks are done, this kind of thing. So this is our system call. It looks pretty simple and pretty straightforward. So the init node is at the top, the ending node at the bottom, and in between it's pretty much linear. If we get a closer look, we can see that first an information data structure is getting filled in, and then later the current process is looked up, and if we go at the end of the function, there is a call to another function called kill something info. So we want to explore this one because it looks like it does the real job. It does not show up. Okay. This does not mean that the function does not exist, but that it's not a global function. So we can confirm that by looking at the file in which it's probably defined. So here we are in signal.c. Let's have a look. Here it is. Okay, if we look at the list of functions exposed by signal.c, we see no kill something info function. So this confirms that the function is static. But nevertheless, we can still explore it. There are two ways of doing this. Of course, we could go with the open menu, but there is a simpler way, because actually every function call is a hyperlink to the activity diagram of the function. Hop. Control plus click opens the activity diagram. So this function looks a bit more complicated, with more complex control flow. So what's interesting in this representation is that we are free to read the function as we want. For example, we can start from the ending node and get back to the beginning and exploring the branching and conditions that lead to the end. Well, let's see what we can deduce from the control flow itself. First of all, on the right, apparently we have a loop. We can see that every node is reachable from every other node. Here we have a condition, here another condition. Here is the top condition. If we have a closer look at it, okay. So every condition in our activity diagrams are binary. So here it's p over 0 or p less than 0. If we look at the manual of system called kill, we can learn that p over 0 means that we want to send a signal to a single process, and p less than 0 means that we want to send a signal to a group of processes. So let's say that we are not interested in the latter case. We can get rid of the branch very easily by double clicking. The function is much simpler now. So we are left with a couple of nodes here, RCU lock and RCU unlock, and in between we have a call to another inner kill function. If we open it, okay, we see that it's a pretty simple function. apparently there is a loop over an RCU section. So with additional knowledge about the synchronization methods of the kernel, we can deduce that the function group send siginfo in the middle is called inside the RCU section, and it's the call is looped until synchronization succeeded. Okay, let's have a look at what we have explored so far. We have gone quite deep in the kernel, but we are still in the same file, signal.c. In this function we have two interesting calls. Do send siginfo, which is probably a function which does the real job of sending a signal, and check kill permission, which is probably where the security checks are done. Okay, if we enter this function, okay, again we have synchronization, lock unlock task, and in between send signal. What does it mean to lock a task? Well, we can have a look. Okay, this function is a bit complicated. First of all, we can see that the init node is not at the top. That's because the entire function is a loop body actually. So I have not much to say about this function. Actually, that's not the part of the kernel we were to explore. Okay. Well. Let's get back to higher level functions. We can get rid of uninteresting branches in the history through the contextual menu. Here is how I delete an entry in the history. So let's get back to send signal. There's an inner function. This function is the biggest we have explored so far. Okay, at the beginning we have a couple of sanity and safety checks. For example, here we check that all the appropriate locks are taken. Then here we have a bit of assembly code. Actually, that's the bug report code to record that we met a bug in the Linux kernel. For example, a lock which is not taken where it should be. Here we have prepare signal, which here we have an allocation. Okay, error handling code seems to be on the left. Also short circuits or error handling early exits. And if we follow on, we have all the details of how a signal is delivered. And at the end, we have trace signal generate. So this is a call to a function to notify, if we have a tracer, to notify it that we have been sending a signal. So let's get back to an earlier function. We want to see how the security checks are performed. So let's enter this function. Okay, valid signal and an error code on the right. Here another error code, another, what are the security checks? Here we have a list. First the valid signal, audit signal, whether a thread is trying to send a signal to a thread in the same process. Here, do we have the right to send this signal? Finally, an interesting function call. This function is part of the Linux Security Module Framework, which is the API used by SC Linux, Arparmor, Blair, etc. to implement custom security policy in the kernel. So all those functions are in fact placeholders, like hooks, which can get called by a foreign module to perform additional security checks to those already performed by the kernel. Here, for example, we see that we look up a field called taskkill in the security ops data structure, and that there is a call to an anonymous function that is a call to a function pointed to by a function pointer. Okay, we have explored quite a lot, and we now have a clear idea of how signal of a system called kill works. So that's all I wanted to show you. I hope you enjoyed the video. Thank you for watching.